Hi, I'm Rohas Nagpal, and in this video we are going to have a look at the basics of the blockchain technology. I'd like to begin with a small disclaimer. This video is intended for the novice viewer and may suffer from errors inherent when a complex topic is oversimplified. The first concept we need to understand is hash functions. A hash function is a mathematical algorithm, so to say. In a simple way, we could say that the hash result of any input is the digital fingerprint of that input. Now, for example, we take the word Sanya written in all small letters. We then run it through the SHA-256 hash function. It returns 64 characters, these alphanumeric characters. If we now change the original Sanya into Sanya with the capital letters, it returns another set of 64 characters, but as you notice, they are different. We take only the first letter as a capital and the others in small, we get another output. Now, one thing that you would have understood by now is the output is always going to be 64 characters because we are using SHA-256. But as soon as we change the input, even by a very small extent, the output changes. If we take a PDF document, which could be, let's say, a 10,000 page document or a 2-page Word document, we would still get the same number of characters, 64, but obviously the characters are going to be different. Now, to give you an example about where hash functions are used, in a cybercrime case, let's say the police has confiscated a laptop. Now the witnesses are going to say that yes, this was the laptop that was confiscated from the criminal. A few years later in court, do you think there is any way in which a normal human witness can say that the laptop that was confiscated on the crime scene and which contained, let's say, 20,000 files, none of those files have been tampered by the police during this 5-year period before the matters come to the court? That's not possible. That is why at the time when the laptop is confiscated, the police would use specialized hardware and software to run a hash function through the entire hard disk, through all those thousands of files, and a 64 character code is generated. The witness would then sign that this was the 64 character code generated at the crime scene. A few years later, when the matter is brought to the court could then have the same hash function run through that laptop. Another set of 64 characters is generated. The witness would then compare and say, yes, it is the correct 64 characters. Then the court can believe that the police have not tampered with the laptop. So this is a real world example of where hash functions are used. You may be aware of the concept of digital signatures. In digital signatures, we actually do not use our private key to sign the original document. The software calculates the hash result of that document, and then our private key is used only to sign the hash. And at the time of verification, the same process is reversed. The reason being that if we actually try to use our private key to sign a large document, it would take too long. Hence, we only sign the 64 character hash rather than signing the entire document. Moving on, a hash function, to summarize, takes an electronic record, whether it's a PDF file, a video, an email, and produces a fixed length output, for example 64 characters in this case. If the information is changed in any way, even a comma is changed in a 3000 page document, a different output value is produced. And there is no way to calculate the original record from the hash. So when I give you a 64 character hash, by looking at it, it is not feasible for you to figure out whether the original was a single word, a blank space, or a 10,000 page document. That is why these are also called one-way hash functions, because we can't really reverse them in a feasible manner. Moving on, let's understand the concept of proof of work. Now let's say we want to control the problem of email spam. The reason that it's so easy for a spammer to send out so much bulk mail is that he simply needs to compose that message and click one button and millions of spam email can be sent out. Now let's try to envisage a scenario in which we are making the spammer pay for every email that he sends. And when I mean pay, not in terms of cash, but we want some proof that his computer has done some mathematical calculation before each email is allowed to go forward. To simplify, let's take an example. We say that for every email that is going to be sent, the sender's email address, the receiver's email address, the date, and a mathematical value called a nonce needs to be concatenated and the hash produced, and that hash needs to satisfy a condition that it begins with 4 zeros. For example, Rohas at primechain.in is sending an email to info at primechain.in on 29th January 2017. So these three pieces of information are put. We put a small delimiter, and then at the end you see this red number starting with 0, 1, 2, 3 going forward. We keep incrementing this number such that when this entire chain is hashed, the resultant hash begins with 4 zeros. Now as you can see, when we take this nonce to be 0, the hash doesn't begin with 4 zeros. So we go to the next step. From 0 we make it 1. We again hash, again it doesn't begin with 4 zeros. So we keep incrementing this 0, 1, 2, 3, 4, 5 till we reach the nonce value 31201, and here we notice that the hash begins with 4 zeros. At this stage, the computer can stop this function, and now along with the email it would send this number. So when the recipient computer receives this email, it knows the sender, the receiver, and the date. It puts this nonce, calculates the hash of this entire string, and verifies, does it begin with 4 zeros? If yes, that email is allowed to go through and it is received. Otherwise, the email is deleted. Now obviously the sender's servers and the receiver servers need to accept and follow this exact algorithm. So both of them know that it is going to be SHA-256 which is used, and the resultant hash must begin with 4 zeros. And to calculate this hash, it must take the sender, the receiver, the date, and the nonce, put it in this order, and separate it by this delimiter. Now as we can understand, computing this nonce for the sender is not trivial. It takes time. In this example, it took 31202 numbers. Why? Because we started with 0. In another case where the date changes or the sender or the receiver changes, the nonce value could be much bigger or much smaller. We cannot really predict what the nonce is going to be. So computing the nonce is not trivial. But verification at the user's end is very, very trivial, because he just has to check whether this particular nonce satisfies this particular condition. To give you an idea what happens in the back end, let's have a look at this. So for Rohas at primechain.in as a sender, info at primechain.in as a receiver, 29th January 2017 as a date, when we use the nonce 0, this is the hash. As we can see, it doesn't begin with 4 zeros. We then increment the nonce to 1, 2, 3, and we keep doing it till we reach a hash which begins with 4 zeros. Moving on, there's an interesting concept called Merkle Tree. Let's consider that we have 4 pieces of data or information. Data 1 could be a PDF file, data 2 could be an email, data 3 could be a movie, and data 4 could be a transaction. We calculate the hash for data 1, for data 2, for data 3, and for data 4. Now we have 4 hashes. We then concatenate hash 1 and hash 2 and produce this hash. We also then concatenate hash 3 and hash 4 and we get this hash. Then we take these 2 hashes, concatenate, rehash, and we get this hash. So irrespective of how many pieces of data there are, our goal is to finally reach one single hash here. We call this entire thing a Merkle tree, and this as the Merkle root. Now moving on, let's have a look at what a blockchain actually looks like. This part here could be considered to be the actual blockchain data, and this could be considered to be the blockchain header. Now every blockchain begins with block number 0, but for this example, let's start with block number 17. Now the header of block 17 contains 4 pieces of information. One is the previous hash, which means whatever was in the header of block 16, these 4 things are concatenated, hashed, and that hash comes here. Second is the transaction root, which is basically the Merkle root of all the data or transactions that are going to go into block number 17. So as discussed earlier, we have 4 pieces of data, for example. We get the hashes. Concatenate the first 2, we get this hash. Concatenate 3 and 4, we get this hash. Then we concatenate these 2, we get this hash. And this final hash, called the Merkle root or the transaction root, goes here. Then we have the timestamp, which could be, let's say for example, when did this block get filled up? And finally, we need to calculate this nonce. So 0, 1, 2, 3, we keep going till we reach a number which, when these 4 pieces of data are concatenated and hashed, the hash begins with 4 zeros. And the moment this is done, we say that block number 17 has now been mined. Similarly, this would have happened in block number 16. This happens in every block except block 0. In block 0, we don't actually follow these conditions because that is the block that is generated by the creator of the blockchain. He may have a very different set of parameters only for that block. For example, he could even give himself a huge reward, but that's not the point right now. As we can see, a blockchain is an ordered and time-stamped record. So this order is very important and is always maintained. It's 16, 17, 18. You can't really change this. And there is a timestamp for every block. In a scenario where a blockchain is used for cryptocurrencies, for example Bitcoin, this particular architecture prevents double spending. Like if I give you a physical currency note, you can't really spend that note twice. You spend it once and it's gone. Similarly, in a blockchain, you can't really spend your Bitcoin twice. The moment you've spent it once, the system gets to know. So whenever you try to make a transaction, it would go back to block number 0 and then it would find out what is the actual balance in your address. So from block 0, it starts computing how many times your address received the cryptocurrency, how many times it spent it, and finally when it reaches the current transaction, it knows whether to allow that transaction through or not. Also, a blockchain prevents modification of previous records because of this chain which is established between blocks. By using hash functions and proof of work, we can prevent modification of previous records. To summarize, while a gold miner digs into the earth to discover gold, a Bitcoin miner would use computational power to calculate hashes. I'm going to refer to Bitcoin for some time because that is the most successful cryptocurrency that runs on a blockchain. In fact, it is Bitcoin that basically introduced the concept of blockchain in the world. So the Bitcoin miner is going to use computational power to calculate hashes. To add an entire block to the blockchain, a Bitcoin miner must successfully hash a block header to a value below the target threshold. Let's try to understand what we mean by this. Suppose we've decided that in our blockchain, a new block should be mined every 10 minutes. Now we know that we can't really predict what the nonce is going to be, so it's not necessary that every block is actually going to take 10 minutes. It may take more or less time. So what the blockchain would do is, every 2 weeks, it would see what was the average time taken to mine a block in the last 2 weeks. Suppose that time is 8 minutes. Well, then the blockchain thinks that the difficulty level is too low. That is why people are able to finish the mining in 8 minutes rather than 10. So it then increases the difficulty level by increasing the number of zeros that a hash should begin with. Again, now this continues for 2 weeks. After 2 weeks, when it now checks, it realizes that it took 14 minutes. That means the difficulty level is too high. So then it reduces the number of zeros. And the system keeps doing this every 2 weeks. Here, of course, 2 weeks just being an example. The ultimate goal being to maintain an average of 10 minutes per block. Then miners spend on computational power and electricity. And in return, they are compensated by way of a reward for each block and transaction fee for transactions that could be in the block. Now in the Bitcoin scenario, this block reward started with 50 Bitcoins a block. 4 years later, it went down to 25. 4 years later, it's down to 12.5. And every 4 years, this reward would halve. This would go on till the year 2140, by when this block reward would become 0. And at that point of time, there would be 21 million Bitcoins in circulation. So the number of Bitcoins are not supposed to go beyond 21 million. Considering the large number of miners in the world today, they usually operate as part of a large pool instead of individuals. Well, this is an example of what a Bitcoin mine could look like. So it's got a lot of very powerful processors that are going to do the mining. This being another example of what a Bitcoin mine could look like. Before we conclude, I'd like to make some points clear. There is a difference between the Bitcoin platform and the Bitcoin cryptocurrency. So the Bitcoin platform is the blockchain or the technology on which the Bitcoin cryptocurrency runs. And the Bitcoin cryptocurrency is what is given to miners as a reward, and subsequently it can be traded by people around the world. When we use the term the blockchain, usually with a capital B, we are talking about the Bitcoin public blockchain. When we talk about private blockchains, we usually use a small b here. We are talking about private blockchains that could be set up by companies, banks, any entity. These private blockchains are usually also called permissioned blockchains. While the Bitcoin blockchain is permissionless, which basically means anyone can join or leave, private blockchains are usually permissioned blockchains. Also, stuff that only a blockchain can do is running cryptocurrencies. In fact, the concept of cryptocurrencies didn't practically exist till the Bitcoin blockchain was released. So, only blockchains can run cryptocurrencies. What is it that a blockchain can do better than other solutions is whenever we require data authentication and verification or securities or other settlements, at that time blockchains are very, very powerful because they are provably immutable. It can be proven in a court of law that the data has not been tampered with. To give you a simple example, let's say there's a 20-year-old person who takes out a life insurance policy on himself. Now, 50 years later, the policy could still be in force. So it should be possible for the insurance company to prove to the court 50 years later that the insurance policy hasn't been tampered with or the conditions haven't been changed. And that is something blockchains can do very well. As of today, blockchains may not be a good solution when we are talking about something like high-speed trading. Let's say on the stock markets where you're doing 1 billion transactions a day, blockchains as of today may not be an ideal solution for that. I'd like to end with the disclaimer we started with. This video is intended for the novice viewer and may suffer from errors inherent when a complex topic is oversimplified. Thanks for listening. If you have any questions, please feel free to email us on info@primechain.in.